Beneath Saturn's shimmering rings and icy shells lie mysteries more profound than we've ever imagined. Hidden worlds where life could be thriving in conditions that challenge everything we thought we knew. Imagine moons wrapped in thick atmospheres or cracking icy crusts, harboring oceans of water, energy, and the raw ingredients for life. These aren't just science fiction scenarios, but possibilities scientists are actively exploring, aiming to uncover whether life exists beyond Earth in some of the most unlikely places in our solar system. If we find even the faintest hint of life or habitability there, it could completely reshape our understanding of life itself and the universe's incredible diversity. Stay tuned, because the secrets of Saturn's moons could be the next giant leap in humanity's quest to find our cosmic neighbors. Saturn's moons and the search for life. Several of Saturn's moons are intriguing candidates in the quest to find extraterrestrial life, primarily due to their unique compositions and subsurface environments. Enceladus, in particular, has captivated scientists because of its icy exterior spewing plumes of water vapor and organic molecules into space, providing a direct window into its hidden ocean. This active cryovolcanism suggests a warm, liquid water environment beneath the crust, which is fundamental for life as we understand it. The detection of complex organic compounds within these plumes indicates the presence of the raw ingredients necessary for life, sparking excitement about the possibility that microbial life could be thriving in this concealed watery realm. Tethys, Dione, and Rhea also offer compelling environments for potential habitability, although their prospects are less active or visible than Enceladus. Tethys' surface shows signs of past geological activity, and its interior might host a subsurface ocean or brine pockets, especially considering the gravitational interactions with Saturn. Dione features a thin atmosphere and signs of tectonic activity, hinting that internal heating could sustain a liquid layer beneath its icy shell. Rhea, while seemingly more inert, could still harbor liquid water in isolated pockets or brine layers, especially if it contains internal heat sources or radioactive materials that generate sufficient warmth over geological timescales. Titan, another prominent Saturnian moon, stands out because of its thick, nitrogen-rich atmosphere and hydrocarbon lakes on the surface. Although its surface temperatures are extremely cold, making liquid water unlikely on the surface, the possibility of a subsurface ocean beneath an icy crust remains plausible. This hidden ocean might contain water mixed with other salts and compounds, creating a potentially habitable environment beneath the surface. Titan's complex organic chemistry, driven by sunlight and chemical reactions within its atmosphere and possibly its subsurface ocean, heightens the chances of finding prebiotic molecules that could serve as precursors to life. The combination of these moons' active geology, internal heat, and chemical richness makes Saturn's system one of the most promising frontiers for astrobiology. Ongoing and future missions aim to probe beneath the surfaces, sampling plumes, analyzing ice, and searching for thermal anomalies to uncover clues about the existence of life. The discovery of microbial organisms or even simple life forms in these alien environments would revolutionize our understanding of life's resilience and the potential ubiquity of life across the cosmos. Each piece of evidence holds the promise of rewriting what we thought was possible about life's origins, persistence, and diversity in the universe. The unique environment of Saturn's moons. Saturn's moons present some of the most intriguing environments for potential extraterrestrial life within our solar system. Among them, Enceladus and Titan stand out due to their unique geophysical characteristics. Enceladus, a small, icy moon, sports a surface woven with fractures and geyser-like plumes that spew water vapor and organic molecules into space. These plumes originate from an underground ocean kept in a liquid state by tidal heating. Gravitational forces from Saturn and neighboring moons generate enough internal friction to prevent the water from freezing solid. The presence of liquid water, combined with organic compounds detected in the plumes, suggests an environment that could host simple life forms similar to those around Earth's deep-sea hydrothermal vents. Titan, on the other hand, offers a distinctive atmosphere rich in nitrogen and methane, much thicker than Earth's and shrouded by a dense haze. Beneath its icy crust, scientists suspect a subsurface ocean of liquid water mixed with dissolved salts and organic molecules. The cryovolcanoes and hydrocarbons on Titan's surface paint a picture of complex chemical processes, possibly akin to early Earth conditions. Methane lakes, abundant on Titan, dynamically interact with the atmosphere, creating a cycle that might support life forms adapted to very different climates and chemistries compared to terrestrial environments. These lakes could harbor microbial life that metabolizes methane or other hydrocarbons, thriving in a liquid interior shielded by the icy shell. What makes these moons especially compelling for astrobiologists is their proven ability to sustain liquid phases, whether water or hydrocarbon, within environments that are inherently extreme. Tidal heating, driven by Saturn's gravitational pull, supplies a steady source of energy that keeps subsurface oceans liquid over geological timescales. This energy source is not just a matter of maintaining temperature. It could also power hydrothermal vents or chemical gradients essential for life to emerge and persist. The possibility that such ecosystems might exist in hidden, dark oceans deep beneath ice shells agitates imaginations, especially since these environments lack sunlight, but could still support chemosynthetic life similar to creatures thriving around Earth's ocean vents. Finally, the unique environments of Saturn's moons challenge our understanding of life's adaptability. The combination of high-pressure, low-temperature oceans in contact with rocky interiors creates a plausible setting for prebiotic chemistry to unfold. Organic molecules, delivered by comets and interplanetary dust, could concentrate in the briny seas, fostering complex chemical reactions. The ongoing discovery of such environments fuels speculation that life could be more diverse and resilient than previously imagined, just waiting for the right combination of elements, energy, and time to spark into existence. Each mission that penetrates the icy crusts or analyzes the plumes adds another piece to this puzzle, inching us closer to understanding whether Saturn's moons are truly habitable or not. Titan, a methane ocean world. Beneath the thick, orange-hued haze enveloping Titan lies one of the most intriguing environments in the solar system. Instead of the familiar waters of Earth's oceans, Titan hosts a vast, cryogenic landscape dominated by lakes and seas of liquid methane and ethane. These hydrocarbon bodies stretch across hundreds of kilometers, creating a dynamic and complex chemical landscape. The cold temperatures, hovering around -179 degrees Celsius, keep these hydrocarbons in a liquid state, and the surface is dotted with organic-rich dunes, cryovolcanoes, and possible subsurface ocean zones. This exotic environment challenges our terrestrial assumptions about where life might exist, shifting the focus toward alternative biochemistries. Scientists hypothesize that beneath Titan's hydrocarbon lakes, a subsurface ocean of water and ammonia might exist, separated by an icy crust. If life has found a foothold here, it would have to adapt to a radically different chemical context, or perhaps rely on entirely different biochemistry. The thick, organic-rich environment at the surface provides a plentiful supply of complex molecules, some of which are crucial ingredients for life as we understand it: amino acids, nitrogen compounds, and hydrocarbons. These could serve as building blocks or fuel for hypothetical microbial communities that thrive in liquid pockets or within porous, icy crusts, utilizing energy sources such as chemical gradients or radiolytic processes. The possibility of life on Titan isn't purely speculative. Some models suggest microbes can metabolize methane or ethane similarly to how Earth organisms metabolize water and oxygen. For instance, these microbes might use hydrogen molecules released through cryovolcanic activity or radiolytic chemical reactions in the ice to produce energy. Such organisms, if they exist, would push the boundaries of known biology, perhaps resembling extremophiles found in Earth's most hostile environments like deep-sea vents or icy Antarctic lakes. The unique blend of organic compounds, liquid hydrocarbons, and potentially accessible energy sources makes Titan an enticing candidate in the hunt for extraterrestrial life elsewhere. An alien ecosystem where life is fundamentally different, but still driven by the same need to harness energy and reproduce. Further exploration, like the upcoming Dragonfly mission, promises to unlock more secrets about this methane world. With its rotorcraft drone capable of hopping across Titan's diverse terrain, scientists hope to sample surface materials, analyze organic compounds, and perhaps even identify microenvironments with the right chemical ingredients for life. While the harsh cold and unfamiliar chemistry present significant challenges, they also make Titan a natural laboratory for understanding life's potential beyond Earth. The idea that some form of life could flourish in liquid methane, perhaps RNA-like molecules, or even simple cellular structures, gives a sense of just how extraordinary and varied extraterrestrial biology could be. In the quiet, icy depths of Titan, the question remains, could life have adapted to thrive in a world so utterly different from our own? Enceladus, water plumes, and subsurface ocean. Jets of water vapor and icy particles erupt from Enceladus's southern pole with such force that they reach thousands of kilometers into space, forming a vast, diffuse plume that has captured the imagination of scientists. These plumes serve as a direct window into the moon's hidden depths, revealing complex chemistry that hints at more than just frozen water and simple salts. The material caught in these jets contains organic compounds, silica particles, and other organic precursors, which are all potential ingredients for life. This discovery was pivotal. These plumes suggest there's a vast, liquid reservoir lurking beneath the icy crust, continuously replenished by geological activity. Beneath the surface, a vast subsurface saltwater ocean is theorized to exist, lying beneath a crust of ice several kilometers thick. Evidence for this ocean mainly comes from analyzing the composition of the ejected plume material, which contains salts akin to Earth's oceanic waters. The presence of hydrothermal activity at the ocean floor, similar to Earth's deep-sea vents, quite possibly creates an environment rich in chemical energy. Hydrothermal vents are hotspots for complex ecosystems on Earth, driven by chemosynthesis rather than sunlight. If such vents exist on Enceladus, they could provide the conditions necessary for life to emerge or survive, using chemical gradients for energy rather than relying on sunlight. This ocean ecosystem, if it exists, would be vastly different in temperature and pressure from terrestrial environments, but it may host microbes or other simple life forms adapted to thrive in extreme conditions. The gravity and radiation environment present challenges, yet life has proven remarkably adaptable in Earth's deep oceans where sunlight never reaches. Scientists speculate that bacteria-like organisms could exist near hydrothermal vents, utilizing chemical compounds like hydrogen and methane, which have been detected in the plumes. The organic molecules observed further support the idea that complex prebiotic chemistry is taking place, potentially leading to biotic processes in this concealed aquatic world. What makes Enceladus especially intriguing is its potential for sustained habitability. The continuous cycling between the ocean and the surface via plumes implies a dynamic environment with fresh nutrients constantly supplied. Unlike planets with stagnant oceans, this exchange could replenish biological material and provide energy sources essential for life. In terms of practical exploration, sampling the plumes gives a rare opportunity to study the moon's interior chemistry without drilling through miles of ice. These delicate signs of potential habitability continue to energize missions like NASA's planned probes, which aim to analyze plume composition in more detail, seeking that elusive signature, be it complex organics or even microbial life, hidden beneath Enceladus's icy shell. Mimas and Tethys, their potential subsurface habitats. Mimas and Tethys, two of Saturn's larger moons, have stirred curiosity among scientists because of their intriguing geological features and the possibility of hidden, life-friendly environments beneath their icy crusts. While both moons are characterized by thick shell-like layers of water ice, their interiors might host more complex systems of liquid water or other solvents, potentially creating niches where life could exist. Evidence from recent observations suggests that these moons may have internal heat sources, possibly sustained by gravitational interactions with Saturn and neighboring moons, which could keep subsurface layers in a liquid or semi-liquid state. The surface features of Mimas are dominated by a massive impact crater known as Herschel, which gives it a resemblance to a cosmic Death Star. Beneath that rugged exterior lies a body that might harbor a layered internal structure with an icy crust overlying a mixed zone of water ice and possibly some silicate material. If internal heating occurs due to tidal flexing, it could generate pockets of liquid water or briny mixtures within the moon. Such environments could, in theory, support microbial life, akin to extremophiles thriving in Earth's harshest habitats. Evidence from other icy moons suggests that subsurface oceans could be kept from freezing solid by a combination of residual heat and the pressure exerted by the overlying ice shell. Tethys presents a different, but equally captivating case. Its surface is marked by a network of deep fissures called wrinkle ridges and a giant valley known as Ithaca Chasma, evidence of tectonic activity and internal stress. These features imply a dynamic interior that might facilitate heat transfer and maintain liquid reservoirs below the surface. Similar to other icy moons, Tethys could potentially contain a salty ocean or briny pockets trapped in cracks and fractures. These habitats might be isolated from the surface, but still accessible to chemical energy sources and potentially microbial life if some form of water-rock interaction exists deep beneath the ice layers. Both moons also feature surface compositions rich in water ice, mixed with other substances such as salts and organic molecules. Over time, impacts and tectonic activity could transport nutrients and chemical energy from the moon's interior to its surface. This exchange could provide a vital energy source for life, should any microbial or more complex organisms have developed in the hidden depths. Ultimately, the fascination with Mimas and Tethys lies in their capacity to host stable, long-lasting environments beneath their icy exteriors, hidden worlds where the conditions, though extreme, might resemble some of the most promising extraterrestrial habitats we have yet to find. Hyperion and Dione, mysterious surface features. Hyperion's jagged, sponge-like appearance offers more than just a visual curiosity. It hints at complex geological and possibly chemical processes that could support life. Its irregular, porous surface suggests extensive erosion by sublimation, where ice transitions directly from solid to gas, creating vast cavities and intricate ridges. Such features could form microenvironments where liquid or vapor phases temporarily exist, offering potential habitats for microbes adapted to extreme conditions. The porous nature might also trap organic molecules or other nutrients, enabling primitive life forms to find sustenance in an otherwise icy landscape. Dione, on the other hand, displays a striking mixture of heavily cratered regions and areas marked by smooth plains, with many features indicative of past geological activity. Its bright, wispy features, thought to be deposits of ice particles blown by Saturn's magnetic field, paint a picture of ongoing surface interactions. Beneath its icy exterior, Dion's slightly warmer interior due to tidal heating could allow a subsurface ocean or liquid layer, potentially harboring microbial life. The surface features, especially the chasm-filled regions and tectonic fractures, might serve as pathways for chemical nutrients to migrate from the interior to the surface, continually renewing the possibility for life-friendly environments. Both moons challenge traditional ideas about habitability, especially because their surface features can trap and preserve organic compounds or provide sheltered niches shielded from radiation. Hyperion's porous surface could act as a shield, protecting potential microbial communities from cosmic rays and solar radiation, while Dion's fractures and cryovolcanic activity could facilitate chemical exchange between its subsurface ocean and surface. Evidence from distant observations suggests that these moons might host transient environments or subsurface pockets where primitive life could exist, even if only in microbial forms adapted to extreme cold and radiation. Ultimately, the surface mysteries of Hyperion and Dione are gateways to understanding Harry Potter-level secrets hiding just beneath icy shells. The irregularities, fractures, and deposits aren't just static features. They could be dynamic habitats or conduits for chemical evolution. As explorations continue, focusing on these peculiar surface features could uncover signs of life or prebiotic chemistry. Given their location around Saturn, incredibly cold and bathed in radiation, the potential for life hinges on these surface features acting as both guardians and channels, fostering environments that challenge and expand our understanding of what it takes for life to emerge and persist in the most extreme corners of our solar system. The role of chemical composition and habitability. The chemical makeup of a moon's surface and subsurface environment forms a foundational aspect when considering its potential to support life. In the case of Saturn's moons, scientists focus heavily on the presence of compounds that could foster biological activity. For instance, water, whether in liquid, ice, or as part of mineral structures, is a central ingredient. Moons like Enceladus and Titan display signs of complex organic molecules intertwined with water ice, raising intriguing questions about their habitability. Organic molecules, especially carbon-based compounds such as methane, ethane, or more complex hydrocarbons, are essential building blocks for life as we understand it. Their presence in the form of plumes or surface deposits hints at rich chemical interactions occurring beneath the surface, possibly in liquid reservoirs or subsurface oceans. Crucial chemical elements like carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur are often under scrutiny because they form the core of biological molecules. On Titan, for example, the thick atmosphere transforms sunlight into complex organic tholins, nasty-sounding but fascinating compounds that could serve as precursors to prebiotic chemistry. The presence of liquid hydrocarbons, particularly methane lakes, suggests a different but potentially rich chemical system compared to Earth's water-based life. If conditions allow, chemical reactions between these compounds could lead to amino acids or other organic precursors within the moon's environment, creating a playground for potential biochemistry in unfamiliar forms. In icy moons with subsurface oceans like Europa or Enceladus, the chemical composition of ocean water becomes especially critical. These oceans are believed to be in contact with rocky mantles, which could trigger hydrothermal activity. Such interactions might introduce mineral catalysts necessary to facilitate complex chemical reactions, including the synthesis of organic molecules. The chemistry here isn't static, it's dynamic, driven by heat and mineral interactions that could concentrate organics or even produce energy sources akin to Earth's deep-sea vents. Turbid, mineral-rich waters that contain sulfur compounds or metal ions could serve as energy sources, fueling any nascent microbial ecosystems that might thrive in these hidden worlds. Finally, the potential for habitability hinges on the stability and availability of these chemical ingredients over geological timescales. The right chemical composition isn't enough if these components are fleeting or confined to extreme environments that are inaccessible. The detection of specific molecules and their ratios, along with understanding how they interact under the moon's unique conditions, could unveil whether these alien worlds harbor the chemical prerequisites for life. As exploration advances, decoding the chemical symphony of Saturn's moons might reveal environments where life, in some form, could not only exist but flourish unseen beneath icy crusts or within thick atmospheres. Energy sources beyond sunlight. Deep within the icy cracks of Saturn's moon Enceladus, liquid water oceans heated from within by gravitational flexing offer a tantalizing environment for potential life. Unlike planets that rely heavily on sunlight, these moons can sustain ecosystems through alternative energy sources. Tidal heating, caused by the gravitational tug-of-war between Saturn and its neighboring moons, generates a significant amount of internal heat. This process maintains pockets of liquid water in a subsurface ocean, offering a stable environment where chemical reactions could produce energy for microbial life. When plumes of water vapor erupt from Enceladus's south pole, they carry organic compounds, possibly the building blocks of life, upward, powered by this internal heat rather than solar energy. Hydrothermal activity represents another compelling energy source. On Earth, such vents at the bottom of oceanic ridges host rich ecosystems thriving without sunlight, relying instead on chemical energy from minerals released during geothermal processes. On moons like Europa and potentially Enceladus, similar hydrothermal activity could exist beneath icy crusts, where water interacts with rocky interiors. These interactions can lead to chemiosynthetic ecosystems, where bacteria utilize energy released from mineral oxidation, such as ferrous iron or sulfur compounds. These chemical gradients could sustain life in environments where sunlight never penetrates, making the presence of hydrothermal vents a promising focus for astrobiological studies. Fuming beneath icy surfaces, radiolysis offers yet another pathway for generating usable energy. Cosmic rays and high-energy particles incessantly bombard the outer layers of these moons, splitting molecules like water and producing reactive chemicals such as hydrogen peroxide, molecular hydrogen, and oxygen. These products can serve as energy sources, fueling microbial metabolisms similar to those found in Earth's extreme environments. In some regions, subsurface lakes or pockets might harbor a chemical soup generated by radiolytic reactions, amplifying the possibility of life that relies solely on internal, non-solar energy sources. The presence of such chemically active zones could be critical in understanding how life could persist far from the sun's reach. All told, the potential for life on Saturn's moons hinges not only on the availability of liquid water, but also on their ability to harness energy from processes that do not involve sunlight. Tidal heating, hydrothermal activity, and radiolytic chemistry form a complex mosaic of possible energy sources. These mechanisms could foster microbial life, thriving in environments where chaos and heat create the perfect conditions for chemical reactions to flourish. Proof that life might find a way in some of the most unexpected corners of our solar system. Geothermal and tidal heating mechanisms. In the shadow depths of moons orbiting Saturn, intense internal heating processes may create pockets where liquid water persists far beneath icy shells. Tidal interactions are paramount here. Saturn's gravitational pull exerts strong, repeated forces on its moons, especially the larger and more irregular ones like Enceladus and Titan. As these moons swing through slightly elliptical orbits, the constant flexing of their interiors generates friction and heat. This tidal dissipation can maintain subsurface oceans in a liquid state, even when surface temperatures are bleak and inhospitable. The discovery of geysers erupting from Enceladus' south pole underscores this phenomenon, suggesting active subsurface reservoirs kept warm enough by ongoing tidal flexing. Geothermal heating, although less immediately visible, plays an equally vital role. Radioactive decay within a moon's rocky core slowly supplies internal heat, and in some cases, this heat can accumulate due to insulation effect from overlying ice layers. For moons like Titan, which possesses a thick, icy crust and potential for a subsurface ocean possibly sandwiched between layers of ice, geothermal energy might create localized environments where chemical reactions occur. These reactions could produce compounds necessary for life, as we understand it, such as hydrogen, methane, or other organic molecules. The presence of cryovolcanoes on moons like Enceladus hints at the existence of internal heat sources that occasionally breach the ice crust, spewing mineral-rich icy plumes into space, an extraordinary sign of active internal processes. The combination of tidal and geothermal heating mechanisms not only sustains liquid water, but also fosters chemical diversity close to subterranean environments. In some scenarios, heat from tidal flexing causes pore spaces within ice shells to warm, creating microhabitats with the potential for chemical gradients, a fundamental condition for life. Moreover, interactions between water and mineral surfaces might generate energy sources for microbial communities, akin to deep-sea hydrothermal vents on Earth. If such ecosystems exist beneath these icy shields, they could be based on chemosynthesis rather than photosynthesis, thriving in darkness and relying solely on chemical energy. Verifying these mechanisms through ongoing and future Cassini data analysis or upcoming missions could open utterly new worlds where the conditions for alien life quietly simmer beneath frozen surfaces. Organic molecules and prebiotic chemistry. The potential presence of organic molecules on Saturn's moons springs from a growing body of evidence gathered through remote sensing and spacecraft missions. Although the environment on moons like Titan and Enceladus is extreme by terrestrial standards, they harbor complex organic compounds, carbon-based molecules that form the foundational building blocks of life. These molecules can originate from a variety of processes, such as chemical reactions driven by radiation, thermal activity, or shock waves from impacts. On Titan, for example, thick clouds of methane and ethane serve as a medium for ongoing organic synthesis, producing a diverse array of complex hydrocarbons. Mysteriously, some of these molecules resemble prebiotic precursors, certain amino acids and nucleobases, found abundantly on Earth, hinting at the universal chemistry that might transcend planetary boundaries. In Enceladus, plumes erupting from the moon's icy surface contain a rich cocktail of organic molecules, salts, and silica particles. These materials come from subsurface ocean, where water interacts with rocky materials, facilitating hydrothermal processes that could mimic Earth's own deep-sea vents. Such environments are thought to foster prebiotic chemistry, where simple molecules could assemble into more complex structures like amino acids or even lipid-like compounds. The presence of organics in these plumes both sounds well with the idea that, if the conditions are right, even a seemingly frozen and icy world could generate the necessary chemical evolution towards life. These molecules are more than just chemical curiosities. They're potential ingredients for life's emergence in environments vastly different from terrestrial norms. On profoundly alien terrains like Titan's hydrocarbon lakes or Enceladus' subsurface ocean, viral-like molecules or precursor organic structures might be forming continuously. Laboratory experiments simulating Titan's atmosphere have produced complex organics known as tholins, which resemble macromolecular organic material. These substances could serve as the raw materials that, under the right conditions, go through prebiotic processes. On Enceladus, amino acids have been detected directly within the jets, and their presence hints that the chemical pathways to life could be actively at work beneath the ice, where liquid water and organic chemistry intersect. It's easy to envision these environments acting as natural laboratories, where simple molecules could gradually assemble into more complex, lifelike organic structures. While the puzzle remains incomplete, the symphony of organic molecules detected around Saturn's moons fires imagination. Their presence suggests that, long before the dawn of life on Earth, similar chemistry was unfolding elsewhere. Prebiotic chemistry, where simple molecules join in complex reactions to form the earliest building blocks of life, might be underway beneath the icy surfaces or within thick atmospheres. The detection of organic molecules in these extreme environments intensifies the possibility that life's chemical precursors are widespread, awaiting only the right conditions to ignite into self-sustaining processes. This universe, in its vastness, might be teeming with molecular experiments, clues left behind in the chemistry of distant worlds that beckon us to discover whether life could truly be an inherent property of cosmic chemistry. Indicators of hydrothermal activity. Beneath the icy crust of moons like Enceladus and Europa, scientists increasingly consider hydrothermal activity as a crucial factor in the potential for life. On Earth, hydrothermal vents are teeming ecosystems where warm, mineral-rich water interacts with the ocean floor, creating a haven for unique organisms that thrive without sunlight. Evidence from Enceladus's plumes, giant sprayings of water vapor and ice particles, suggests that similar hydrothermal processes may be occurring beneath its surface. These vents could supply the chemical energy necessary to sustain microbial life, utilizing metals and sulfur compounds that are abundant in such environments. Detecting signs of hydrothermal activity in these distant worlds involves looking for specific indicators embedded within their geological and chemical makeup. For instance, the presence of certain minerals, like clay or silica deposits, often points to water-rock interactions typical of hydrothermal systems. On Enceladus, analysis of the plume particles has revealed complex organic molecules and salts, both of which could form through hydrothermal processes. This hints at a dynamic geothermal system beneath the ice shell, similar to Earth's black smokers or white smokers, where heated water dissolves minerals from the rocky crust and then deposits them as vent chimneys. The chemistry of the plumes also offers clues. The ratio of hydrogen, a byproduct of water-rock interactions, to other compounds like methane or carbon dioxide can help infer ongoing hydrothermal reactions. Elevated levels of hydrogen gas, for example, strongly indicate that water is interacting intensely with mineral-rich rock, creating a constant source of free energy that microbes could exploit. Furthermore, the presence of certain sulfide minerals detected in plume particles suggests volcanic or seismic activity beneath the surface, both of which could power hydrothermal systems. These kinds of chemical signatures, if confirmed through future missions, would bolster the argument that these moons contain exotic, yet potentially habitable environments. In the realm of astrobiology, the potential for life hinges significantly on such hydrothermal energy sources. On Earth, some of the earliest life forms emerged from hydrothermal vents, making these environments prime targets for seeking signs of extraterrestrial life. The interaction of warm water with mineral-laden rocks creates organic molecules and provides stable energy gradients, conditions that could allow simple life forms to develop. The prospect of detecting living microbes, or even just biosignatures, molecular remnants of past life, in plumes or sediments would be revolutionary. It suggests that, far from the warmth of sunlight, worlds like Enceladus might still harbor the basic ingredients for life, sustained by the intense warmth and chemistry of hydrothermal systems deep beneath their icy shells. Conditions necessary for life to thrive. Beneath the icy crusts of moons like Europa and Enceladus, the potential for life hinges on a delicate balance of environmental factors. Liquid water is universally regarded as the backdrop for life as we understand it. On these moons, gravitational interactions with their parent planets generate tidal heating that prevents their subsurface oceans from freezing solid. This continuous energy input maintains a stable environment where liquid water can exist for prolonged periods. Such oceans are kept in a delicate equilibrium, thick enough to resist rapid freezing, but not so hot as to destroy complex chemistry. The presence of chemical nutrients, particularly elements like carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, is equally vital. These elements, fundamental building blocks of life, may be delivered via hydrothermal vents or ocean floor interactions with rocky interiors. In fact, evidence from Enceladus's geysers suggests that organics and other complex molecules are being steam-vented from its subsurface ocean. These compounds can serve as energy sources or raw materials for microbial life, which could thrive in the dark, high-pressure environment deep beneath the icy shell. Environments where hydrothermal activity occurs are especially promising because they offer both heat and chemical gradients that could energize biological processes. Temperature regulation is another critical factor. Though the surface conditions of these moons are extreme, the subsurface oceans are buffered from surface temperature swings by thick ice layers. These layers insulate the interior and help maintain a temperature range conducive to life, likely just above freezing, comparable to the temperatures found near Earth's deep-sea hydrothermal vents. Such conditions promote chemical reactions necessary for life by providing a stable environment where molecules can interact over extended periods without rapid degradation. The presence of mineral-rich ocean floors could further support this, offering a foundation for complex chemistry and potential energy sources through mineral oxidation. Lastly, energy sources beyond just heat are essential. In environments devoid of sunlight, energy must come from internal processes, radioactive decay, tidal flexing, or hydrothermal activity. These sources create gradients that microorganisms could harness, such as redox reactions involving sulfur compounds or methane. The detection of methane signatures on moons like Europa suggests active organic chemistry, possibly driven by microbial communities similar to those found deep in Earth's oceans. If such ecosystems exist, they would be remarkably resilient, relying on chemosynthesis rather than photosynthesis, and could survive in conditions that once seemed inhospitable to any form of life. Future missions and technologies in exploration. Advanced space exploration techniques are steadily evolving, bringing us closer to uncovering whether the icy moons of Saturn could harbor extraterrestrial life. Missions like NASA's proposed journey to Titan and potential future probes targeting Enceladus are designed with cutting-edge technologies that could detect signs of life hidden beneath thick layers of ice. Robotic landers equipped with sophisticated drills may soon be able to penetrate icy crust to reach the subsurface oceans believed to lie beneath, possibly revealing ecosystems thriving in complete darkness and extreme pressure. The design of these missions incorporates miniaturized laboratories capable of performing complex chemical analyses on site. These instruments aim to identify organic molecules, energy sources, and chemical gradients, key indicators of potential habitability. Some concepts even envision the use of heat-generating drills powered by nuclear energy to access deeper layers where life could exist. Advances in telemetry and autonomous operation make it possible for probes to survive the intense radiation environments and harsh cold of these moons, transmitting valuable data back to Earth with reliability that was unthinkable a decade ago. Emerging technologies, such as artificial intelligence and machine learning, are poised to revolutionize exploration. AI algorithms can analyze incoming data in real time, helping scientists identify promising biosignatures or anomalies that warrant further investigation. These systems could guide robotic explorers through unpredictable terrains, reacting dynamically to unexpected obstacles or discoveries. Moreover, new propulsion systems, like solar sails or ion thrusters, may enable more extensive surveying of Saturn's complex moon system, increasing the chances of pinpointing habitats capable of supporting life. Finally, international collaboration and innovative mission architectures are pushing the boundaries of what's possible. Sample return missions, where material from subsurface oceans could be collected and brought back to Earth, are being seriously contemplated. Such endeavors rely on precision landers, drills, and containment systems designed to prevent contamination, ensuring pristine scientific analysis. Truly, the technological landscape for exploring Saturn's moons is advancing rapidly, with each new breakthrough offering a tantalizing glimpse into the possibility that life, perhaps microbial or more complex, could be hiding in some of the most extreme environments known in our solar system. Implications for extraterrestrial life. Saturn's moons, particularly Enceladus and Titan, have ignited scientific curiosity because of compelling evidence suggesting they might harbor conditions suitable for extraterrestrial life. Enceladus, with its icy shell and subsurface ocean, ejects plumes of water vapor and organic molecules through cracks in its crust, hinting at a dynamic, possibly habitable environment beneath. The presence of complex organic molecules within these plumes pushes the idea beyond simple microbial life. One could envision microbial ecosystems thriving in the dark, pressurized depths of the ice, akin to extremophiles found in Earth's deep oceans near hydrothermal vents. The implications are profound. If life can exist in Earth's extreme environments, why not beneath an icy shell on another world? Titan presents a different, yet equally enticing context. Its thick atmosphere and surface lakes of liquid hydrocarbons create a chemical environment vastly different from Earth, but still potentially capable of supporting life forms based on chemical systems we haven't fully understood yet. Hydrocarbon-based life, sometimes called methanogenic, might rely on chemical energy sources available in Titan's methane and ethane lakes, and perhaps in the organic haze enveloping the moon. The presence of complex organic molecules, precursors to life, detected in Titan's atmosphere and on its surface raises the possibility that prebiotic chemistry could be taking place in these alien environments. Discovering any form of life here would radically expand our understanding of the diversity of living systems and challenge the way we define habitability itself. The potential for alien life on Saturn's moons also emphasizes the importance of habitability beyond just Earth-like conditions. Where conditions are extreme by human standards, life might evolve along radically different pathways, utilizing solvents other than water or energy sources beyond sunlight. This broadens the scope of astrobiology, prompting scientists to consider environments previously dismissed as inhospitable. If microbial life exists in the subsurface ocean of Enceladus or within Titan's hydrocarbon lakes, it might share little more than a fleeting resemblance to terrestrial life. It could be metabolically distinct, utilizing chemical gradients or radioactive decay, and existing in complete darkness or under intense pressure. Such discoveries would hint that life is more resilient and adaptable than traditionally assumed and could be far more common throughout the universe. The discovery of extraterrestrial life, or even a mere presence of complex organic molecules, in these moon environments would be monumental, reshaping our place in the cosmos. It would suggest that life can originate and persist in a diverse array of planetary settings, not limited to Earth's temperate, water-rich habitats. Such advancements would also influence future missions, targeting subsurface oceans or thick organic atmospheres as prime sites for exploration. Ultimately, finding life on Saturn's moons would redefine the boundaries of what we consider possible, laying foundational knowledge that fuels dreams of a universe teeming with biology in forms and places we are just beginning to imagine. Deeper beneath the icy crusts of Saturn's moons, promising environments for extraterrestrial life might exist in ways previously unimagined. Europa and Enceladus, in particular, have captured scientific attention due to their subsurface oceans of liquid water, a key ingredient for life as we know it. Evidence suggests that these oceans are not just static reservoirs, but dynamic systems with the potential for chemical interactions that could support microbial life. Meanwhile, Titan presents a different scenario. A thick nitrogen-rich atmosphere with liquid hydrocarbon lakes on the surface and complex organic molecules in the mix, possibly creating the right conditions for a form of life adapted to an entirely different chemistry. One of the most intriguing prospects lies in hydrothermal activity within subsurface oceans. Tidal forces exerted by Saturn create enormous pressure and heat on these moons' interiors, possibly driving volcanic or hydrothermal vents much like those found on Earth's ocean floors. Such vents could provide energy sources for chemotrophic microbes, which do not require sunlight and instead thrive on chemical reactions involving minerals and hydrogen compounds. For example, if water interacts with rocky cores rich in olivine or other silicate minerals, it could generate hydrogen gas, a vital energy source. The potential presence of simple organic molecules in these environments, coupled with heat and mineral catalytic surfaces, hints at a plausible scenario for the emergence of life. Additionally, organic compounds observed on Titan and in Enceladus's plume spark excitement. The Cassini-Huygens mission revealed structures teeming with complex organic molecules, including amino acids and hydrocarbons. These molecules could serve as building blocks for life, or at least indicate prebiotic chemistry occurring in the moon's environment. On Titan, thick atmospheric processes generate organic aerosols that settle onto the surface, potentially forming a rich chemical stew. If some of these molecules find their way into subsurface lakes or oceans, perhaps transported by hydrothermal activity, Conditions might be ripe for the evolution of microbial ecosystems even without the presence of sunlight. Such environments could resemble, in extraordinary ways, some of Earth's deep-sea ecosystems, where life persists around vents and mineral-rich sediments. The possibility of life on Saturn's moons hinges on still unconfirmed, but plausible, conditions that merge heat, liquid water, and organic chemistry. What makes these environments particularly tantalizing is the prospect for discovery in terrains that remain largely unexplored. Technologies such as ice-penetrating radar, autonomous submersibles, and future landers could, someday, identify signs of microbial activity or biosignatures directly. Each piece of evidence would deepen our understanding of how life could develop in the most unlikely locales of the solar system, expanding the horizon of possible habitats in the universe and pushing the boundaries of what we consider to be truly alien. As we wrap up our exploration of Saturn's moons, it's astonishing to think about the possibility that these distant worlds might harbor alien life in hidden, icy oceans beneath their surfaces. The idea that life could exist in such extreme, unknown environments sparks a sense of wonder and curiosity that pushes us to look even further. From the sulfuric vents on Enceladus to the subsurface lakes of Titan, these moons challenge our understanding of where life might thrive beyond Earth, reminding us that the universe is full of surprises waiting to be uncovered. Imagine detecting signs of microbial life or even more complex organisms thriving in these alien oceans, an echo of life's resilience and adaptability. It's a thrilling prospect that keeps scientists and explorers eager to send missions and gather more data, inching closer to answering one of humanity's most profound questions. Are we alone? If this story captivates your imagination, stay tuned because the journey is just beginning. Future missions to Saturn's moons promise new discoveries, and first they'll be here to share every exciting update. Until then, keep looking up and dreaming about the possibilities that lie beyond our skies. The cosmos is full of secrets, and together, we're on the edge of uncovering one of its greatest mysteries.